Hi, and welcome to my Physics Online video lecture series. Today's lecture, we're going to be talking a little bit about lateral as opposed to angular magnification. So in some sense, we're talking about just magnification in general. So what is magnification and what is it all about? Well, in my previous videos, I actually introduced the lateral magnification. So lateral magnification, we often represent with a capital M, and what it is defined as is the height of the image versus the height of the object, or the length scale of our image versus the length scale of our object. Basically, what this means is that if I have, let's say, a person or something to look at, and I look at them through a lens. Maybe I'm looking through the lens of glasses or something like that. And the end result is that the glasses form an image of that person. Let's say the image is moved out here somewhere, let's say. And now the person is like this. That image is now taller or larger than the person themselves actually were. Okay? So this right here would be like the height of the image, and this right here would be the height of the object being imaged. Now, what about angular magnification? So angular magnification basically means that the image is taking up a different fraction of, let's call it, your field of view than the object originally would have taken up. So angular magnification, we often use a lowercase m to represent. And so lowercase m, angular magnification, is actually defined as theta of the image divided by theta of the object. Now, to understand what this is talking about, let's say that again, this is my eye. It's some distance away from the lens. And let's say that I am looking at this person right here. Okay. In so doing, this person kind of subtends some angle, theta O, for object that I'm looking at. But the image is going to subtend a different angle. So this angle right here being subtended by the image is not the same as the angle that was being subtended by the object. This right here is theta I. Now in this case, they're both pretty similar. But let's draw another scenario where, let's say, the lens is over here somewhere and the eye is maybe right here somewhere that we're looking at everything with. And let's say now that I have a person who is, or object or whatever that I'm looking at, that's represented right here. And now let's say that the image is maybe like 2 times farther away than the original object, which means that the image should also be 2 times bigger than the original object. So now I have an image of this person that I'm looking at that is 2 times taller than the original person was. Okay, and that 2 times taller, this right here is still dO. This right here is still dI, which is negative 2 dO in this case. And now let's look at what angle is being subtended by each of these two. So this person right here is subtending this angle. We'll call this theta. Theta O for object. And now this one right here is subtending a new angle which is theta I for image. And you'll notice that because I'm looking at this object through an optical device that is some distance away from my eye. Maybe it's a telescope, for example. Maybe this little lens represents like a telescope of some sort. And maybe I stick my eye up to the telescope, but remember that the telescope is a set of lenses. And so maybe like the effective point that we call the optic, if we reduced it to like one equivalent optic, is some distance away from my eye. And everything is being imaged according to where this effective lens is. Now, granted, I could say that the effective lens is this last one, but I could always hold off a little bit and look through it like this. Same difference. Because the lateral magnification is at a ratio of how far away is the image and the object from the lens rather than from my eye, my lateral magnification and my angular magnification factor will not necessarily be the same. Among other things, with a telescope, one of the interesting effects is that very often you'll get a lateral magnification that is less than 1, but an angular magnification that is greater than 1. So telescopes, one of the things that they do is they actually make the thing you're looking at smaller, but they also bring it a lot closer to you. If I'm looking at the moon, and I look through the telescope and I see a moon that has an image this big, this is a lot smaller than the actual moon is. I think everybody watching this can agree. This is smaller than the actual moon is. But if instead of appearing to be 250,000 miles or 380,000 kilometers away, if that image of the moon appears to be, let's say, 2 meters away, then an image this big, but 2 meters away, looks a lot bigger. I can see stuff a lot better than the real moon that is many times bigger than this, but is also many, many, many more times farther away. So angular magnification basically has to do with how much of my field of view is the thing now taking up compared to what the original object took up. If my field of view of the moon, if the moon takes up, this much space out of all this screen, and then I look at an image of the moon, and the image of the moon appears to take up this much space for the same screen, well, I can see more details on this moon, even though the image itself laterally is smaller than the moon itself. Okay, so that is angular magnification. Now, what about a microscope? What does a microscope do? Well, a microscope actually does a little of both. You get some angular magnification, you also get some lateral magnification. So the actual image of the things you're looking at under a microscope is bigger than the object itself. If I'm looking at a cell under a microscope, maybe the cell is 10 microns across. It's a pretty big eukaryotic cell. It's 10 microns across, but the image of that object could be 600 microns across and also move to a location where it those 600 microns take up a larger fraction of my field of view than something that is the original cell, essentially. With the microscope, you actually have to do a little of both, because the cell itself takes up very little of your field of view, but it's also tiny enough that regardless of how close or far away you hold that cell, you're not going to see any of the details, or many of the details, really any. So when you put it under the microscope, it blows up how much of your field of view the thing takes up, but it also sort of like blows up how big everything is on the image, so that it's of size scales that you can actually resolve with your eye, regardless of how close or far away it is. How much of my field of vision does a cell have to, or how close to my eye does a cell have to be to take up, let's say, like this much compared to the screen of my field of vision? Well, practically touching my eye, but if I take a cell and put it right on my eye, I can't necessarily see it. And that's not just because I don't have very good accommodation limits, or because I don't have that level of accommodation limits with my eye. It's because the cell is also too small. So microscopes, you need both kinds. Telescopes, you need more angular magnification, and your lateral magnification may be actually less than 1. So that's that subject. That's angular magnification. That's lateral magnification. And I hope that you enjoyed this brief explanation.